In this video, we're going to be talking about section 3.5. That's transformation of graphs. That includes translations, which includes stretches and compressions, shifts up, down, left, and right, and reflections across both the x-axis and the y-axis. This is a lot of material and a lot of different tiny details that have to be remembered in order to solve these problems correctly. And I will warn you, I find some of this material quite hard. If you want to bring yourself, your best self to this work, make sure you don't do it when you're too tired, because that will just be an exercise in frustration. Let me share my screen with you and we'll get started. The first thing that I want to do is I want to talk at least a little bit about the process of figuring out how a transformation is affecting the graph of a function. But to do that, I need to have graphs of functions. We have what we call common functions to memorize, or toolkit functions. You can find these inside of D2L. I have a handout to help you figure out what the primary points on the toolkit functions are. Let's take a look at the D2L shell so you'll know where to find them. In D2L, go ahead and click on the Content tab. When you click on the Content tab, which is found here in the upper left, it will take you to the table of contents. Scroll down on the table of contents on the left until you reach something that says Professor D's material just for you. Click on that particular link. Scroll up to the top. You'll see a series of handouts that I've written over the years to help my students figure out different things. There's an entire folder on factoring review if you need to review factoring at any time. There's an algebra cheat sheet, which has sort of, well, let's just take a look. The algebra cheat sheet has all the basic properties and operations that we study in an algebra class: distance formula, complex numbers, exponent properties, and so on. It goes on and on for several pages. Once we've clicked on something, we can always get back to where we were by following the breadcrumb trail at the top. I'll click back on Professor D's material just for you. After the algebra cheat sheet, you'll see I have one on linear inequalities and absolute value, which we studied in a previous section. And then we have the common functions to memorize, the toolkit functions. I also have two complete files on graphing functions with translation, stretches, compressions, and reflections. This is what we're studying at section 3.5, these two handouts here. This gives you more examples that you can go by to help you figure out the solutions to the problems. I'll also go through the homework for you. First, we're going to click on common functions to memorize, which are called the toolkit functions. These are the functions whose shapes and basic points you should have memorized. There's a reason I call it common functions to memorize. I don't often tell my students to memorize things, but when I do, I mean it. You really do need to know these by heart. The constant function, of course, is just a horizontal line at y equal to some number value. Here, y equal to 3. That's our first common function we memorize. Then we've talked about lines before, and we've graphed lines using the slope-intercept form of a line. We need to know how to graph lines and how to get points off of a line. The identity function is a special line, and it has a name just for itself. The identity function is the function where if you put in 5, you get out 5. It is itself, hence the name identity function. So that's the one that has points like -2, -2, 0, 0, 1, 1, 2, 2, 5, 5, 10, 10, pi, pi. This is the graph that will cut quadrant 1 and quadrant 3 in half at a 45-degree angle on a scale of 1 to 1. That means that the x-axis is divided in the same way that the y-axis is divided. The next toolkit function that we want to look at is a quadratic function, and we've studied these before as well. When we're looking at x squared, remember that x squared graphs as a parabola. It's really important that you memorize the basic points on a parabola. There are 3 that I recommend that you know for sure: the origin, which is where the vertex is. That's going to be the lowest point of an upward opening parabola right here. Then there are two pairs of points that go with each other. When you square one, you get one, and when you square -1, you get one. So that's right one, up one, and left one, up one. You need to remember those pairs of points that are reflections of one another across the y-axis. Now, what do we mean by reflection? That means that we're folding the graph on the y-axis, with the y-axis being the crease in the piece of paper. And as we watch the two pieces of paper come together, we can see that the graph actually touches itself on both sides. That's what we mean by reflection, truly like a reflection in a mirror. The other pair of points are right 2, up 4, and left 2, up 4. You need to remember these basic 5 points on the parabola. The next toolkit function that we have is the cubic function. The basic cubic function is x cubed. It goes through the origin at 0, 0. Because 1 cubed is 1, we also have the point 1, 1. But -1 cubed is not 1, it's -1. So we also have the point -1, -1. When we cube 2, we get 8, which is up here. And when we cube -2, we get -8, which is down here. I like to think that these are John Travolta in Saturday Night Fever, right? Yes, okay, I'm cracking you up, I know. But that is basically what they look like. Memorize the basic 5 points, which you see over here. Higher degree polynomial functions we'll study later this semester. They're not really a toolkit function, so I'm not going to focus on them here. But they're here for you to study later on when we come to polynomial functions. This information be helpful for you at that point. The next real toolkit function that we have is the absolute value function. It is not a polynomial function because of the absolute values. It has a sharp corner. Polynomial functions don't have sharp corners. It's shaped like a V, and the basic one is the absolute value of x. It is the one that has the sharp corner at the point 0, 0, rises to the right along the identity function 1, 1, 2, 2, 3, 3, 4, 4, and so on. But to the left rises along y equal -x. That's -1, 1, -2, 2, and so on. You'll want to memorize these basic 5 points, or better yet, just memorize that it is the one that's at a 45-degree angle in quadrants 1 and quadrant 2. The next toolkit function that we have is the square root function. The square root function to me kind of looks like somebody swimming where they're bringing their arm over their head in the American crawl. So when they're coming like this, it kind of comes over like this. So you see this shape right here. The normal square root function is the square root of x, and it has a point here at the origin. Basically, the square root of x is half of a sideways opening parabola. So it's like a parabola opening sideways, but we cut off one of the arms. So it's the upper arm of the sideways opening parabola. And this point here at the origin would be the vertex of it. Then again, we have right 1, up 1, but then we have right 4, up 2. It sort of reverses the order of the parabola. Instead of right 2, up 4, it is out 4, up 2. And that's because it's the inverse operation. You'll want to memorize at least some of these points. I recommend the first 3, 0, 0, 1, 1, and 4, 2. Rational functions are, again, not really a toolkit function, but they are something we're going to focus on later this semester, I believe in chapter 5. So when we get to chapter 5, you'll want to come back to this sheet to look at polynomial functions and rational functions. Let's see if there's another toolkit function. I think that's pretty much it, but I do have another sheet at the end, which goes through the basic points again in a slightly different way. These are just the toolkit functions until we get to the rational function at the bottom. I hope this helps you to learn what the toolkit functions basically are. These are the ones that we're going to be using in this section. Again, let's go over what our basic toolkit functions are, just so that you can make note of them in your notes. We have a constant function, we have a linear function, we have the identity function. We won't use lines very much in this particular section because they don't make very good pictures. When we change them, they don't transform too much. They still end up being lines. The ones that we'll primarily focus on are the quadratic equation, which looks like a parabola for sure, a cubic function, which looks like John Travolta, and then, of course, skipping the polynomial functions, we have the absolute value function, which looks like a V, and the square root function, which looks like the upper arm of a sideways open parabola, or someone swimming doing the American crawl. Those are the basic toolkit functions. Let's now talk about what happens when we try to transform one of these toolkit functions. I'm going to start with the square root of x, and I'm going to give you some notation for you to learn about the effect of transformations on the graph. What's happening in the graph is we're moving from something that looks like f of x to something that instead looks like a times f of b times x plus c, all in parentheses, plus d. In other words, we're looking at the original function here, which might be our toolkit function like the square root of x, and we've transformed it somehow by introducing some more elements. Now, what is the effect of each of these elements? Let's take a look at them one by one. What happens when we have a times f of x? Well, that might be something like 3 times f of x. If our toolkit function is the square root of x, then what happens when we multiply this by a 3? Remember, f of x represents y, so this is a stretch on the vertical by a factor of 3. We call this a vertical stretch by a factor of 3. Some things to note about this is that the 3 is written outside the notation. It's not inside the parentheses where the x is. If it's outside the notation, like the a and the d, then it affects the y, which is the vertical. So a and d must be vertical transformations of some kind, and they are. Now, what would happen if instead of a 3, we had a negative 3? We would still have the vertical stretch by a factor of 3. But we would also have what we call a reflection. Now, what's a reflection? This would be where we are taking the image and folding it on one of the axes and producing the mirror image on the opposite side of the axis. This is a reflection across the x-axis. Why? Because it's outside the main operation, outside the function notation. So it's affecting the y value. You're taking the graph and you're reflecting it over the x-axis like this. You're folding it where the x-axis becomes the crease in the piece of the paper. What's going to happen to the values when we look at this square root of x? Let's graph it in Desmos and let's see the effect of what happens. On Desmos, I'm going to graph y equal the square root of x. Here's our picture down here. Now our scale is way blown up, so let's scroll in. Remember that you can use the mouse wheel to scroll in. If it gets off center, left click and hold, and then drag it back to the center where you want it. It's still out pretty far. I'm going to click on some points and see if they'll stay on the picture. That's 1, 1, and that's 0, 0. Let me plot the other points so that we can see them. Let's label each of the points, and then we can click on 0, 0, which I think will stay on the picture if I can click on it long enough. Now let's take a picture and let's paste this over here so that we can do some experiments on it. Coming over here, when we paste in our picture, we can tell that what's happening now is that we are reflecting the picture across the axis and multiplying the y values by 3. So instead of the y value being at 1, 1, the y value gets multiplied by 3, so it becomes 1, 3. On this one, the y value would become 4, 6. Again, multiplying the y value by 3. Let's take a bigger picture so we can reflect it appropriately. Now, when we look at this, remember what we're trying to do. Our toolkit function, f of x, was equal to the square root of x. And we took it and we multiplied by a 3, which multiplies each y value by 3, and then by a negative. What's that going to do? The negative reflects across the x-axis, and the 3 multiplies the y value by 3. If I multiply 0 by 3, I still get 0, and when I fold on the x-axis, it stays put. But the point 1, 1 gets reflected over here and comes down to 1, 3. And the point 4, 6, I multiply the 2 by the negative 3, and I get negative 6. In other words, what I've done is I've stretched this in the vertical direction. It's sort of like a piece of taffy where you take it and you stretch it, or maybe one of those bands that you get in physical therapy where you're trying to stretch it out. It's a stretchy piece of plastic. Now let's take a look over here and see what it looks like when we graph that. Remember that the negative 3 is outside the main operation, and that puts it like this. Here's our graph right here. Let's click down here to see where the point 1 went. If I can get it on there, you can see that it became 1, negative 3. Let's click over here when x is equal to 4, and we see that the value became negative 6. This is the effect of A on the graph. Let's go back up here to our original statement here. When we have this, we want to know the effect of the other pieces as well. Let's keep using the square root toolkit function, and we'll take a look at another change. What about this b that's on the inside and this x plus c? This is the part that I personally find really difficult. The b always messes me up. Let's start with just x plus c, which is more common, and then we'll look at the effect of the b. The first thing I want to look at is taking the function f of x, which is our toolkit function square root of x that you see here, and I'm going to rewrite it as f of x plus 4. What does that do to the original graph? Well, first thing to note is that the plus 4 is inside the notation. It's not outside the notation like the a was. Because it's inside the notation, it affects x, which controls horizontal movement. So this is going to affect horizontal movement. Because it is affecting x and it's inside the main operation, it always does the opposite to what you think it would do. I would think a plus 4 would move it to the right 4, but because it's inside, it does the opposite and moves it to the left 4. What does that mean for our toolkit function? Let's revert back to the graph on Desmos and see what happens to our graph. I'm going to take the previous point, our previous graph, negative 3 square root of x, off our graph. Now we want to know what happens when we move it left 4. What that does to each value is it takes the x coordinate and it moves the x coordinate left 4. So the point 0, 0, which I think would be better if I went ahead and typed it in so it shows up all the time, gets moved to the left 4. So it will become negative 4, 0. And the 0.11 also moves left 4, so it becomes -3, 0. And the 0.42 moves left 4, so it becomes the 0.02. In other words, I pick up the whole graph and I move the whole graph over and put it back down 4 to the left. This is sort of like a sticker. When you peel the sticker off and you move it over and you set it back down, but it's exactly the same size and the same shape, it's just in a different location. That's exactly what's happened here. When I try to graph this one, this is going to look like the square root of x plus 4. Notice that it moves all the points to the left. 0, 0 went to -4, 0. 1, 1 went to -3, 1. And 4, 2 went to 0, 2. It just took the same graph exactly as it was before, peeled it off, and stuck it back down in a different place. That means that what's inside here, the C, affects left and right motion. If it is a plus number, it goes to the left. If it is a minus, it goes to the right. That means that if I am taking f of x and I'm transforming it, and I write f of x minus 7, then this actually moved to the right 7. Let's take a look at what that would look like. You'll see over here that it shows up at this point. Each point has been moved to the right by 7. Again, we're applying this to the original, which is the one here, which I think I'll make black so that it shows up a little better and contrasts with the other two. I find that part of it to be pretty straightforward and not as difficult as the next part. This part, to me, sort of makes sense. When it's outside the main operation, it affects y and does what I think it would do. When it's inside the main operation, it affects x and always does the opposite to what I expect. What is the effect of the b? The b is the more difficult part, and we'll start with a simple one. Well, simple for this type, which is not simple at all. And then we'll move to something more complicated. We're going to transform our function square root of x, and we're going to rewrite it as 2x. Now, again, notice that the 2 is inside the notation. That means it affects x and not y. The 2 being multiplied by the x is going to be either a stretch or a compression. When it's a number multiplied, it's a stretch or a compression. That's what we saw up here when we were looking at multiplying the outside by a number. This became a stretch. What do you think would make it be a compression? Yes, multiplying by a number less than 1. If I multiplied this by a 1/2, instead of stretching the graph, it would compress the graph vertically. On the inside, however, it does the opposite to what I expect. And since it does the opposite, I would expect the 2 to stretch it, but it's affecting x, so it's the opposite to what I expect. So this must be a compression by a factor of 2. That means it's going to compress the graph horizontally this way. The weird thing is that a horizontal compression has the same effect on the graph as a vertical stretch. Again, a horizontal compression and a vertical stretch have the same effect on the graph. Looking over here, what it's going to do to each of my values, and I'm going to turn the other pictures off for a moment so that we can see what they look like, is it's going to take each x coordinate and cut it in half. So 0 cut in half would still be 0, so this point does not move. 1, 1 takes the x coordinate and cuts it in half, so it becomes 1/2 1, which shifts to here. 4, 2 will cut the 4 in half and shift it to 2, 2, which would be here. Let's take a look at that function and see if what we expect to happen is what happens. Here's our new function, which I'm going to color blue. When we're looking at this one, notice that what we have right here is 0, 0 still at the same point. What was at 1, 1 gets moved over here to 1/2, 1. Again, it cuts the x coordinate in half, but leaves the y coordinate alone. What was at 4, 2 gets cut in half and compressed, and it becomes 2, 2. The effect is to squish the graph horizontally, like grabbing the sides and pushing them together. And it has the same effect as vertically stretching it. So it does meet our expectations. Now, what if we have a bunch of stuff on the inside? Remember that we have this B quantity x plus c. Let's take a look at what happens when we have a transformation that's more complicated on the inside. In fact, the most complicated I can imagine. If I have something like 2x plus 8, what is this going to do? You might think that this was going to be, again, a compression because it does the opposite to what I expect by a factor of 2, and a shift to the left, again, doing the opposite to what I expect by a factor of 8, but you'd be off. It is going to be a compression by a factor of 2, but the 2 is affecting this number right here. We have to factor the 2 out of the 2 terms on the inside of the parentheses before we know how far left or right it's moved. This is going to give me instead a 2 times x plus 4. So this is going to be a horizontal compression by a factor of 2 relating to the 2 that we see here. And we're going to have a shift. This x plus 4 shifts it either left or right, doing the opposite to what we expect because it's inside the notation, inside the parentheses. Since I expect a plus to go to the right, it goes to the left. And this will be a shift left 4. Let's see what that effect has on the graph. We'll go ahead and add in here our 2x plus 8. What happened to the graph? Well, first off, the 0, 0 got shifted to -4, 0. So the effect was it cut the x value in half, half of 0 is still 0, and then shifted it to the left 4. What about the 1, 1? First, it cut the value of x in half, which got 1/2, and then it shifted it to the left. That means that it ends up at -3.5, still y value of 1. What about the 4, 2? The 4, 2, in this case, got cut in half and became a 2. That would put it at 2, 2, but then it got shifted to the left. So it becomes -2, 2, if I can get it on there. I'm having a little trouble. My hand's not steady enough. Well, you may just have to trust me on that one. I can't seem to get it exactly on there. Does that make sense? I hope it does. Now let's make it even more complicated. This is the worst of all possible situations. What if that factor on the x were negative? What effect would that have on the graph? Let's start with something simple, and then we'll go to something more complicated. Let's say it was just a transformation where the original toolkit function got transformed with a negative x on the inside. The negative on the inside multiplied by the variable is going to be a reflection like a negative on the outside multiplied is. However, because it is on the inside, it's got to affect horizontal. So it's got to be a horizontal reflection. To reflect horizontally, we actually fold on the y-axis. So it's going to take the picture and fold sideways so that it becomes a reflection across the y-axis. Let's take a look at that picture now. Here it is. You can see that it has been folded so that the y-axis is the crease of the piece of paper, and that these points would line up as we touch each other. What happened to the individual coordinates? Again, if I can get my hand to be steady enough, what happened to 1, 1 is that the x coordinate got multiplied by a negative and became -1, but with the same y value of 1. 4, 2 then, if I can get my hand to get on the point, became -4, 2. Again, multiplying the x coordinate by a negative, but leaving the y coordinate alone. What would happen now if we multiplied by a 2 with a negative? Let's insert the 2 here. Think for a moment about what you expect to happen. The 2 should be either a compression or it should be a stretch. It's inside the operation, so it does the opposite to what we expect. I would think it would stretch since it's bigger than 1, so it must compress. So it's going to compress by a factor of 2. What was at 1, 1 is going to end up at 1/2. If I can get it there, 1. So then the reflection gives it a -1/2. Then we have the 4, 2. First we reflect, which would put it at 4, and then we compress, which would put it at 2, -2, 2. I hope this helps you to understand what the effect of the inside part of this would be. Let's take a look at one of the other pieces. The other piece that we have left is the plus d. The plus d is not inside the parentheses that follow the function notation f, so it's not affecting x. It's outside of the notation and outside the main operation. That must mean that it affects the y value. Then, because it affects y, it should do what I think it does. I think adding a number would shift the whole thing up, and subtracting a number would shift the whole thing down. Let's try it and see. Let's take our toolkit function, square root of x, and let's transform it to be f of x plus 3. Yep, it does exactly what I thought it would. This is a sticker again. When we're not stretching and compression, it's basically like a sticker that you peel off and set down somewhere else. The value 0, 0 left the x coordinate alone, but shifted the y coordinate up 3. 1, 1 again left the x coordinate alone, but shifted the y coordinate up 3 and became 4. The point 4, 2 leaves the x coordinate alone at 4, but shifts the y coordinate up and becomes, oh, I don't think I can get right on it. Something about that point just doesn't want to come out. Well, piffle. I thought I had it. There, 4, 5, finally. Okay, now that we've gone through the effect of all of these changes, let's actually look at the homework and see what happens there. I'm going to break this video into 2 parts, the basic explanation, which we've just finished, and then the homework problems. I hope you'll watch both parts because this is really difficult material and it will take both parts to really understand what's happening. In the next video, which is 3.5 part B, we'll take a look at the problems.